Okay, welcome everyone to my talk, Fake It Till We Make It, the art of Windows user space emulation. My talk is going to be in English because unfortunately I don't speak Spanish, but I hope you can still understand me. There should be translations down there, so I hope everybody will be able to follow. First of all, who am I? My name is Maurice Heumann, and I'm a DRM developer at a company called Vibu Systems in Karlsruhe in Germany, and we're doing all sorts of licensing stuff. We're doing obfuscation technologies, software protection, and all sorts of things. In my free time, I reverse engineer and bypass a lot of DRM software. So I, for example, bypass Steam CEG, which is used in older Steam games. I've also bypassed Arxan, which is used in Call of Duty, I think also GTA 5 and older versions of Fortnite. And recently I have also analyzed and broken de novo in Hogwarts Legacy. And if you want, you can follow me on Twitter. The agenda will be like this. First of all, I'll explain what I mean by the term Windows user space emulation and what the applications are. And the deeper we go into the talk, the more technical it will be. But I hope you will all be able to follow. I will present existing solutions, and then my implementation. There will be a demo that will hopefully work, and then a few final words. So Windows user space emulation, what's that? In general, emulation, or the idea of emulation, is to run code on a virtual CPU. So instead of running it on the real hardware, on your real CPU, you simulate a CPU, and then you run your application, for example, your ROM, on the virtual CPU. And the idea is to simulate all the hardware around it. And the benefit you get is that the emulator has full control over the executed code. And we'll see later why this is so important. And Windows user space emulation in general is the idea of running a process, an application, an exe file inside an emulator without having a real operating system, without having a kernel underneath. So the operating system and the kernel is simulated within the emulator. The neat thing you have inside the emulator is hooking points, or rather the emulator allows to create hooking points. For example, you can intercept any kind of memory access. You can intercept reads, writes, executions, and all sorts of accesses to memory. But also special instructions, when they're executed, can be intercepted. For example, a Syscall or a CPU ID, RDTSC, all those special interesting instructions. They can all be intercepted using those hooking points. And what's also very interesting is that the emulator also offers a way to detect when a new code path is being executed, which can be pretty helpful, for example, if you want to create a fuzzer and you're interested in coverage feedback. So all sorts of hooking points are enabled using the emulator. But the question is, what can it be used for? What are the applications? And my personal interest is the DRM analysis, and I like to break the DRMs, but unfortunately, modern protection is super strong. So it's really, really strong. And often there is strong obfuscation, there is anti-tampering, anti-debugging, so there is no real way to debug protected applications. So static and dynamic analysis is almost impossible. It never works. But using an emulator, and especially all those hooking points, you have an easy way to create your own analysis framework, your own tooling, and the emulator allows to intercept all external communication, so any kind of hardware access, any kind of memory read, all the things that DRM applications use to bind licensing features. You can intercept all that using the emulator. But you can also trace the execution flow. If you want to deal with obfuscation, if you want to break that, then you can trace that. And emulation was key for my de novo analysis, but I'm not going to talk about that. Yeah, another very interesting application is vulnerability analysis, especially black box fuzzing if you don't have any kind of source code but still want to perform fuzzing on an application. Then you can use an emulator because, first of all, it's very easy to randomize the input you give to an application. You can change registers, you can change the memory, all that. But a nice thing is that you can also save and restore the state of the emulator at any given point. So you can let your application run to the point of interest. For example, if you want to fuzz a special function, you can randomize the input, create a snapshot, and then perform your fuzzing iteration. And when it's done, you can just restore to the beginning and perform the next fuzzing iteration, adjust the input. So it's a very efficient way to perform black box fuzzing. And due to those new code path hooks, you get the coverage feedback that, for example, dynamic instrumentation or other instrumentation tooling would give you if you have the source code. But using the emulator, you don't need the source. You just use the hooks, and you immediately get all the feedback for the coverage. And the execution is always predictable. It's always repeatable because the emulator always behaves the same. And this is nice. So if you found one interesting input, found one vulnerability, it will always be reproducible in the emulator. What emulators are already used for, as far as I know, is malware analysis. So that's pretty similar to DRM analysis. You can analyze the malware using the hooking points, and all the external communication can be intercepted. Just like the execution flow, they can be traced. But again, from what I am aware, emulation is already very common in malware analysis. And I think the reason for that is that malware is usually pretty simple compared to big business applications. So what they do, they talk to the internet, to some control server, they encrypt your hard drive. There are a few Syscalls and API calls used, but they usually don't display user interfaces and have some complex logic requiring a lot of support from the emulator, which is probably the reason why it's already widely adopted. One thing that I really dream about is using it for mobile gaming, because theoretically it would allow to port applications and games to your mobile phone. But of course, that means that there's a lot of work needed. All the UI-related stuff needs to be supported by the emulator. And maybe the performance is trash for the gaming, or maybe it's only suited for old games, but it's still a dream I have that one day I can run all my old games on my phone, and maybe we'll get there. But yeah, for now, it's still a dream. There are, of course, existing solutions that already do the job of emulating. And one thing that I have used a lot is Killing. It's really a great framework. It emulates all sorts of architectures, all sorts of OSs. So it's not only made for Windows, but also for Linux, macOS, and it supports pretty much every architecture you can dream of. There's also Speakeasy and Dumpulator, which is rather made for emulating mini dumps and crash dumps, but in a sense, it's also a user space emulator. But the thing is, all those tools, they're written in Python. It's a great language, but it's slow. And emulation in general is already slow, and if you add Python on top of that, you don't get a lot of more speed. And when doing DRM analysis, I need a lot of hooks. For example, when I analyzed de novo, I had to hook every memory read, and that really costs a lot of time. Every memory access needs a context switch into the Python environment, and that is really slow, which is why I need speed. And I decided to write my emulator in C++, or rather in native code. Maybe one day I can port parts to Rust, but for now it's written in C++. There are also other solutions, for example, Bini or Unicorn PE. But the disadvantage that I see is that they emulate on an API level. That means that they load the application into the emulator, but instead of loading all the Windows DLLs, for example, they provide an implementation for every API and every Windows DLL. And in certain scenarios, this is great, But the result is that those emulators are very incomplete because there are so many APIs, so many DLLs out there, and re-implementing every API call, every DLL, it's so much work that I have not found an emulator that is rather complete. And of course, it's very error-prone. Every re-implementation can contain bugs. And for example, killing, I found a few bugs there. And another reason is that many Windows APIs, for example, they are not very consistent. For example, there is an API get username, which returns a null-terminated string, and then there is one get Windows directory, which returns a non-null terminated string, for example. So there are many inconsistencies that one has to respect when re-implementing all the APIs. And some of those solutions did not respect them. And this is why I want to reuse all the DLLs that are on my system. They're already there, the code is written. It works as good as it can because it's the reference we have. And I want to reuse all those DLLs during the emulation process, which is why I made my own. So the architecture, or rather the implementation, looks like this. And on top, you can see an x86, x64 emulation layer, which deals with replicating the Intel CPU. And I'm not doing that. I'm using the Unicorn emulation framework. Maybe you know it. It's based on QEMU, and it's actually reasonably fast because it uses something called TCG, which stands for Tiny Code Generation, and it's basically some kind of JIT mechanism which just in time compiles the emulation code into CPU architecture compatible code, and it's a good basis. Then, of course, there's an OS awareness layer which focuses on re-implementing all the Windows behavior, and that's actually my own implementation. That's the work I had to do. And the idea is to essentially implement a virtual kernel to emulate on Syscall level instead of on API level, just like the other projects. I emulate on Syscall level, so every Syscall there is re-implemented outside the emulator. So there are different components involved in that process. Of course, there needs to be a PE loader, which loads all the DLLs and applications. There needs to be some component that is responsible for memory management. Of course, the syscalls need to be implemented. And exception handling needs to be done. And threads must be implemented on top of it. There are some orthogonal components like a debugger or some state management tooling. They are not really relevant for all the emulation, but the debugger was really helpful because there's so many bugs you can make while re-implementing the syscalls. And first of all, let's start with the PE loading. In general, what are portable executables? They are the exe files you can find on Windows. They are the DLL files, and they get mapped into memory by the kernel. There is a syscall responsible for that. It's nt-map view of section, and the kernel essentially maps all the headers, the nt headers, DOS headers, and whatnot. It maps the section, the text section with the code, data section, and it applies all the permissions that those sections have, and it also applies the relocations, depending on where the library is mapped in memory. But what it does not do is resolving the imports. That's done in user mode by ntdll, and also calling DLL main is done by ntdll, which is nice because then I don't have to do it. And the executable itself, so the process you start and ntdll, they are always mapped at the process start, but all the other DLLs, of course, they are mapped on demand via the ntdll. The second component that's relevant is the memory manager. Unicorn itself has a basic understanding of memory, so it knows what memory is. It can map memory ranges, and it also supports permissions like reading, writing, and executing. But there are a lot of more types of memory that exist in Windows. For example, you can reserve memory. That means an application can reserve a range of memory without actually owning that memory. So it just has the address space, but there is no physical memory behind that, so it can technically not access that memory. And there is a second type called committing, which is responsible for allocating physical memory that backs this reserved memory space in the background. And there is also a concept of guard pages that exists in Windows. So if you access a guard page, then there is a violation triggering and all sorts of different types that are not supported by Unicorn, which means that we have to implement it on top of Unicorn, but that's actually fairly doable. But there is, apart from the different types of memory, there's also certain sections and special areas that one needs to deal with. For example, there is this thread environment block, which is a special region of memory that contains thread-specific information. For example, it contains the thread ID, it contains some TLS, so local storage for each DLL, and all sorts of thread-related things. There is also the process environment block, which is the same just for the entire process. So it contains the command line information. It also contains a list of all loaded DLLs and all sorts of process-related things. And there is this special segment called K-user shared data, which essentially is a section which provides quick access to important data. Because syscalls in general, they are rather slow. You need the context switch and the kernel has to deal with it. And if you need very frequently accessed data, for example, the current time or some processor information, doing that through a syscall is pretty slow, which is why the kernel maps this region into every process at this specific address you can see there. And it contains all sorts of frequently accessed data, like the OS version and all the processor capabilities and stuff like that. And of course, we need to provide those memory regions through the emulator as well. And but that's it. The most important and of course the most time-consuming part of everything is supporting the syscalls. And in general, what is a syscall? What do they look like? And here is an image. I hope you can read it. It's an excerpt from the NTDLL, and especially it's the syscall NT-open-file, which is responsible for accessing files. And the way it works is by first loading the syscall ID into the EAX register, which is, in this case, it's hex 33. And then, let's just ignore the right part, it performs the syscall, which is essentially the context switch, the part where the kernel performs the requested task. The syscall itself passes the application passes all the relevant arguments in the registers and on the stack, so the syscall can take arguments. But in general, that's what every syscall looks like. At the time of preparing this talk, there were 409 regular syscalls inside the NTDLL, and there were about 1,500 UI-related syscalls within the Win32 UI DLL. And to implement those in the emulator, we can use this syscall instruction hook that Unicorn provides to essentially intercept every execution of the syscall instruction. Then we exit the emulation process, perform whatever task the syscall has to do, and the application works. The tricky thing, though, is to figure out which ID maps to which syscall. And here in the example, we could see that NT-open-file is hex 33. But the issue is that all those IDs, they can vary between different Windows versions, they can change. So the real deal is, how can we find those IDs? And the obvious thing that would come into mind is to disassemble the example we saw before and to essentially find the move instruction and then to find the syscall instruction. But that's quite a lot of work, and I didn't want to do that. So there is a neat trick. You can filter all the exported functions from NTDLL that starts with a prefix NT or with the prefix ZW, they're the same. And you can sort them by their address. So you can sort them, as you can see in the screenshot. Those are the exported functions as seen through IDA. And the order of those functions matches their Syscall IDs. So if we sort them, the first one is NT-access check, and it has ID 0. The second one is NT-worker factory work, whatever, it has ID 1, and so on. So the fun thing is that this works for NTDLL and Win32UDLL, and it saves a lot of work by finding and mapping all the names to their IDs. The real task now is to implement all of them one by one, and that's really a lot of work. There are about 2,000 syscalls to implement, and of course I'm not done yet. Many of them are related to the I/O stuff. There is a lot of registry-related syscalls. There is some RPC stuff, some remote process communication syscalls. There's event handling, and there are so many different types of syscalls, and it's really, really a daunting task, but I'm not going into detail there. So most of the syscalls, they're self-explanatory. So NT-open file opens a file. Everyone knows what happens there, so it's not really interesting to talk about that. One thing that's also important is exception handling, because applications in user mode can trigger exceptions. For example, there can be memory violations, there can be invalid instructions or breakpoints in general, and those exceptions are usually handled by the kernel. So the CPU sends a signal to the kernel, it handles it, and then it forwards everything to the application, and the application has a chance to deal with it. It can handle the exception, it can also just die, but there are all sorts of things the application can do. And the way it works is that the kernel invokes KI user exception dispatcher, which is exported by the NTDLL, and then from there all the exception handling process goes on. And it looks like this. I really hope you can read that. It receives a few arguments on the stack, so it receives an exception context, which essentially contains important data related to the exception. So there's, for example, the exception ID, there is some additional information. For example, during an access violation, there is the address where the exception happened and what kind of memory access it was, if it was a read access, a write access, whatever. There is also a context structure which holds the entire CPU context, so all the registers at the time of the exception. And what happens within KI user exception dispatcher is that all those arguments are forwarded to RTL dispatch exception, and the implementation in there deals with performing all the unwinding. It calls the exception handler, and it deals with all sorts of exception-related stuff. And there is really a lot of things going on under the hood. And because we just load NTDLL, we don't have to deal with all the things that are happening there, unlike, for example, killing, which has to re-implement the entire unwinding process, which can be very complex. There are, for example, so many different types of exception handlers in Windows that exist. There is frame handler 4, frame handler 3. There's stack cookie-related handlers, which perform unwinding. And there are so many different implementations, and you would have to respect and re-implement all of them, but I don't. I just load NTDLL and I'm happy. And the way it works in the emulator is by hooking all kinds of interrupts and violations. Unicorn also provides an interface for that. And then I just build the exception record and the context record on the stack. Apart from that, there is also a machine frame on the stack. There are also a few other things on the stack, but that's not really interesting here. And then we only have to invoke KI user exception dispatcher, and that's it. Exception handling just works, and there's not really any much more to do. And that's very easy, because when using killing and having to re-implement all those things just to get the application to run, it can be really frustrating, and just using what's there, using the DLLs on the system makes life so much simpler. But the worst thing of everything is threads. Sadly, Unicorn has no awareness of threads. It doesn't know what threads are. There is nothing that helps you to implement them. And that's also very sad. But that means that then a custom abstraction is needed. And there are two different ways to implement those. For example, you could use scheduling or real threading. The scheduling works pretty much like a round-robin scheduler. So as you can see in the graphic below, there is one thread working for, let's say, n instructions, and then the second thread gets context switched into the emulator, works for n instructions again, and then the next thread starts running and again until the application ends. And the way it works is that all those threads, they share one emulator, and the consequence of that is it's very predictable, so the application always behaves the same. There are n instructions being executed, always n, and then you switch. But that's also very slow, because you only make use of one host thread, so your CPU is not using all the threads that are available. But being predictable can be important in certain scenarios. But for all the other ones, there's real threading, and the idea is quite obvious. You just map one emulator thread onto one host thread, and that means that you also have one emulator instance per thread. So every thread has an own emulator, an own CPU context. The only issue is that you need to somehow share the memory, because a memory access in one thread has to be reflected in the other one. And the benefits of that is that it's really fast, because the more cores you have, the faster the application runs. But it's also unpredictable. You never know if thread 1 is faster than thread 2. And for example, in fuzzing scenarios, it can be important to be able to reproduce your input. So you really have to decide on which kind of mechanism to use. But both are there, both work, and that's nice. But there's also other things related to threading. For example, the way they work. And on Windows, it starts with an APC call called LDR initialize thunk, and this is the first thing that happens on a thread, and it essentially performs initialization. It runs, for example, all the DLL main functions from every loaded DLL. It performs all those TLL callback work. It sets up all the TLS storage and does pretty much all the initialization, which is nice, because then again, we don't have to. And it ends with the Syscall ZB continue or anti-continue, which switches the context into the function RTL user thread start, which is the actual thread. So this is the entry point of each thread. It runs whatever function you, for example, passed to create thread to be run there. And yeah, that's how threading works. And of course, we need to re-implement that in the emulator, at least the part where those functions are being called. Aside from those components, of course, there is state management, which is not strictly needed for the emulator, but it's very, very, very helpful in almost all scenarios. Again, the emulator should be able to store and restore its emulation state, and this can be done in two different cases, in two different types. The first one is serialization, and the way it works is by serializing the entire emulation state, so all the memory, all the registers, every map module, the entire Syscall mapping, so the mapping from name to ID, the entire process context, every state that lives within the emulator can be serialized. And the result you get is a byte stream, and this can be very helpful, for example, for DRM analysis. For example, when you've set up your analysis framework, you set up your hooks, and then you notice that you made a mistake, your hook is wrong, your logging is bad, then you just store your current state, the current state of the emulation, you get your byte stream, you adjust your framework, you recompile everything, and start up the emulator, and you can just restore the state using that byte stream, and you're back at where you were, without having to run everything again, because depending on how big your application is, for example, modern games can be half a gigabyte, and emulating those can be slow, and being able to restore the state while adjusting the framework can be very helpful and speed up the analysis process a lot. The other type of state management is snapshots, and the idea of snapshots is to save all the volatile emulation states. So all the things that change throughout the execution, they get saved. For example, memory, but only the incremental changes. So everything that happened after the snapshot is registered, all the registers, of course, but things like the process context, the command line, things that are static throughout the execution of the process, you don't need to save them. And the benefit of that is that taking snapshots is a whole lot faster than serializing the entire state, but it only works within the emulation process. So if you stop the process, stop the emulation, then your snapshot is gone. And the main use case, of course, is fuzzing. If you want to restore, you want to perform the next fuzzing iteration, then you use snapshots because you're still in the same process environment. And now we come to the pretty much most important thing of this talk. It's the debugger. Even if it's so simple, implementing all those syscalls is so hard. Even if it sounds simple, being able to debug the emulator is really it's really the key for the analysis. And I chose to implement the GDB serial protocol. It's a simple text protocol over TCP. Maybe also other things, but the way I did was a TCP protocol, and it allows to read and write all the registers, to read and write the memory, and it also supports controlling the execution, so you can perform normal execution, you can perform single stepping, everything you know in your normal debugger can be done using that protocol. And luckily, it's supported by many debuggers. For example, GDB supports it, obviously. Then LLDB supports it, but it has a few extensions, so it's not all that simple. VS Code supports it, and most importantly for me, IDA Pro has an extension to support the GDB serial protocol. And the way it looks in the emulator is that the debugger of choice, so the one you want to use, sends a command to the emulator, and inside this emulator, there is this GDB handler, which has full control of the emulated process. So it forwards all those commands, it sends the request to change the register, it can write the memory, but it can also read the state of the emulated process. So it can read the memory, it can read the registers, and then it responds, the emulator responds with the information and sends it to the debugger. And that's enough talking. I think we should now try to show how it works. I hope you can see my screen. I have prepared a small application called protected.exe, and as the name implies, it's protected, using a self-made DRM solution, because obviously I can't show existing DRM solutions. I don't want to get sued again. So it's a self-made DRM. And if we run the application, we can see loading hook DLL. Just ignore that. That was for a different talk. The first thing it does, it calculates a checksum. And I can tell you it's the integrity of the application. So the protected exe verifies its own integrity at runtime. And then it checks the file name. So it checks if the application was launched with an expected file name. And if both things matches, then the program is running. And now we can try to copy the application. And if we run it, we can see that the copy protection system prevented copying the application. It detected that the file name has changed, and then, of course, it runs, but it says something is wrong. And in a real-world scenario, the application would behave differently. It would maybe crash, or it wouldn't just perform the task you wanted to perform. There are many different ways this could manifest. But, of course, the checksum still matches. We haven't touched or modified the application. And when analyzing applications, the first thing I do is I throw it up in IDA. So let's just do it. And we can see that it starts with the place that invokes the main function. And when we take a look at main, we see that, I can maybe zoom out a bit. I hope you can read it. But we can see that it's really complex. And of course, it's just scam. I coded it to look like that. But in a real-world scenario, it would be very complex. There would be many obfuscation techniques active. And doing static analysis on modern applications that are protected is usually super hard and not very, you will probably not reach your goal. Hope I can zoom in back again. So we see that static analysis won't lead anywhere. So the next thing I would try is to perform some dynamic analysis so we can start to run the application. And as we can see, we don't see anything because it stopped. So we try to set a few breakpoints. For example, we set a breakpoint after the main function. And once we run it, we can see in the output that, of course, the file name matches, but the integrity has been violated. And the reason this is the case is that breakpoints modify the application code. They modify the instructions at that place to insert a breakpoint instructions. There are also different types of breakpoints that exist, but let's just focus on this one. And that means that this application itself protects itself from being debugged just by having an integrity check active. So doing dynamic analysis is not really helpful. But we still have our goal in mind, so we want to be able to copy this application. So the thing is, how do we know, how does the application figure out its file name? So one way, for example, would be to search the imports, and I hope you can read it. But one example or one possible way to do that on Windows would be to check get module file name. So we can just search the imports if there is a get module file name. But as we can see, there is none. It just imports get module handle. If you can't read it, just believe me, it doesn't import get module file name. So another way to do it would be to read the first argument that's passed through the command line, but I can assure you it does not do that. So we're left hanging there. We don't know how does the application perform the protection. We have no way of analyzing it. Static analysis is too complicated. Dynamic analysis doesn't work because of the integrity check. So the only thing we can use now is emulation. So I guess let's fire up the emulator. And I think we can maybe start by running it in the GDB mode. And you will see that it's essentially waiting for a GDB connection. So we can switch IDA Pro to connect to GDB. So IDA Pro in this case will connect to the emulator. And if we do that, I hope it works. Yes. We will see that it breaks on the entry point. So this is our LDR initialized stunk from DLL main. And we can just run the application. And we can see all sorts of interesting output coming there. And our breakpoint triggered. And this is really the application being debugged in the emulator. So it's not running on the host process, it's the emulator. And that's super nice and super helpful for all the development. But also to be able to analyze this protected application. So as we can see, this is the output of the application in light blue. And we can see that the checksum is still matching what was expected. So the breakpoint we set in the emulator does not affect the application. So it's very nice. The application has no way of detecting that it's being debugged except from using some kind of side channel stuff. But the regular mechanisms, the anti-debugging stuff, doesn't work in the emulator because we're not debugging the application, but rather the emulator provides a debugging environment. And that's super nice. But of course, the file name is still wrong. So we can check what the application or what the emulator printed. And we see a lot of gray text. This is all the syscalls the application performs, and usually those are not really interesting. That's why they're not colored. We can see all the DLLs that are being loaded and that are being mapped and where they're being mapped, but that's usually also not very interesting. But once we scroll down, we can see some yellow stuff. And the yellow lines, they mean that the application itself executed some API call, some exported function from a different DLL. And if you're familiar with Windows, you know that these are usually not interesting. Those are the C runtime calls that are executed before the main function. And we can see that here argc and argv are retrieved through the runtime. So here is probably where main starts executing. And we can see the first puts call being executed. And then we can see a load library call, and we see that it's this hook DLL that I told you to ignore that is being loaded, but we still see it in the emulator, so it's very nice. There was no additional setup needed, it just prints everything we need to know. But the green thing is where it gets interesting. This is where we see that the application performs integrity checks, because we see that the executable itself is reading from its own text segment, and this is usually something that no regular application does. So reading from your own text segment is in general suspicious, and the emulator shows us what is being read and where it's being read, and then we can see byte by byte of the entire text segment is being hashed. But the most interesting part is this blue line. We can see that an inline syscall called anti-query information process is being executed by protected-copy.exe. And for those of you who don't know what query information process does, it queries information about your process, and it can also query information about the file name. And doing syscalls outside of NTDLL or Win32U is especially suspicious, which is why the emulator highlights it. So what we can do is we can copy this address, stop the debugging and go to that address, and we can see within the application there is a syscall being executed, and now we know just by running the emulator how the application protects itself from being copied. And if we trace that, we see that it's IDA-Pro is already hanging, but yeah, we see it somewhere within this huge tree of code. But we don't have to stop there, because as we know, the emulator supports hooks, so we can just start to patch the application if we want to know what happens if we feed it the original file name. So we can do just that. The emulator provides a way of adding a syscall hook, and the first thing we do is we read the syscall ID and we translate it to its name, so EAX holds the ID, and then we translate it to the syscall name. If it's not anti-query information process, we just bail out. We don't care about anything else. And then we check if within anti-query information process we are reading the image file name. And if so, we can patch the execution. So instead of reading the original file name, we can feed the expected file name and then skip the execution of the original syscall instruction. So we can try to do just that, but this time without the debugger. And what we can hopefully see is that this pink line prints that we are patching this syscall. And in the output, we can see that protected.exe now matches protected.exe, even though the application we ran contained the copy at the end. So this is very nice, and the emulator offers a real neat and quick way of analyzing applications, just like one would love to by doing dynamic analysis. Okay. So that's it. That's the demonstration. And thank you. But I'm not done yet. You can stop clapping. I'm not done yet. I have a few final words remaining, but I'm happy that the demonstration worked. The nice thing is that emulation is pretty fast, even though emulation in general is slow. So hypervisors, for example, that abuse the CPU features, they're much faster. But using those JIT technologies, using the tiny code generation, emulation is reasonably fast and can be used for all those scenarios. And the hooks, they provide a very extensible analysis interface using the memory read, write, execute hooks, using the instruction execution and the code coverage for fuzzing can really provide a very good foundation to create your own framework. And of course, it can be helpful for DRM analysis, for malware research, for security research, and all sorts of things. But my project is still in development. It doesn't even have a name yet, so if one of you has a good name, feel free to suggest one. I may open source it at some time, or maybe I turn it into a commercial product, who knows, because it's really a lot of work and I don't have much time to work on it. But there is also, of course, a lot of work left to do, because I lied to you, the threading part is only partially implemented, it's not fully done yet. And there are, of course, hundreds, if not thousands, of Syscalls left to implement. I have not done any of the UI-related stuff. And I would love to add some kind of scripting interface so you can still use Python and maybe also JavaScript with Node.js or so to create your scripting or your framework environment using those scripting languages and the benefits they provide. And I, of course, eventually want to replace Unicorn because, first of all, its license is not so nice. And there are a few things that are not so nice about Unicorn. It does a few things in a weird way, and maybe I can replace it. There are a lot of interesting projects, for example, Icicle. It's written in Rust, and maybe I can switch to that. Who knows? But for now, that's it. Thank you very much, and now you can clap. Are there any questions?
Vale, sé que estáis ahí, ¿eh? Por los gritos y esas cosas. ¿Alguna pregunta? En inglés, por favor, que nos intentemos...
Yes, please, in English.
Bueno, si no es en inglés, pues hacemos el esfuerzo. ¿Por allí? A ver, cuidado que grito, ¿eh?
Vigets, what is the challenge you approach when you are dealing with user space emulation, but you are not jumping to kernel space emulation? Because I do believe that you could work not only with DRM, but also with kind of anti-cheats engines that could help with your project to get kind of bigger goals. Is there any obstacle you saw during your implementation?
No, not really. Of course, it could be used for anti-cheats. The only issue is that nowadays, I think most of the anti-cheats, they make use of kernel drivers. And my project only focuses on user space emulation because that's what I need. But of course, there are anti-cheat solutions that are implemented using user mode technologies, and analyzing those would definitely be possible. I just tend to put anti-cheat in kind of the same category as DRM because the technologies used are often just the same. You have some anti-debugging and anti-tampering, and it's definitely not the same, but from an analysis perspective, it's the same, and you can do it. If it's a user mode anti-cheat, of course. If it's a kernel mode, then I don't support that. Maybe one day I can extend the emulator to support that, but it's not what I need at the moment.
Last question, do you have a release date estimation for your project?
No, not yet. I'm sorry. I prepared the talk, and I actually planned to hold a different talk, but then I started doing this project, and I thought it might be an interesting talk, so I started to hustle and to continue the development, but it's really a lot of work, and I don't think that in its current state it makes sense to release it, because it only supports basic scenarios. I try to implement more and more Syscalls, but of course that takes a lot of time. It takes less time than doing the API call way, but I hope I can release it very soon, but I don't know when.
Thank you.
Any other questions?
¿Alguna pregunta más? Ah, mira, ahí abajo. Ay, bueno, bajaré mejor que subir.
Yes. Is there the possibility to have memory access conflict when executing the emulator?
It depends. Are you referring to the threading model or just in general?
No, just in general.
I don't think there is, because the way Unicorn implements memory is just as it exists on Intel CPUs, so the caching behavior is the same. So I don't think there is any conflict that arises for the emulator specifically. If your application has multi-threading and it just doesn't care about doing proper synchronization, then of course your application will also be broken in the emulator. But in general, I don't think there should be any kind of memory access issues.
Thank you.
¿Alguna pregunta más? Seguro que arriba, ¿eh? Eso sí, así. ¿Ah, no? No. Pues otro fuerte aplauso para Maurice.
Thank you.